Today, we're decoding the hidden language of proteins using a truly groundbreaking new AI model. It's a revolutionary deep learning approach called Rprot Vec, and honestly, it is completely changing how we calculate structural similarities in biology. Our roadmap for today covers the protein structure bottleneck, enter Rprot Vec, inside the AI architecture, putting models to the test, accelerating drug repurposing, and finally, the future of discovery. We're going from a massive biological roadblock straight through to discovering hidden cures. Section 1, the protein structure bottleneck. So to really understand what a protein does in our bodies, its actual function, we absolutely have to know its three-dimensional structure. Form dictates function, right? But we hit a massive roadblock here. Based on the protein databank, we actually only know the 3D structures for less than 0.1% of proteins. Think about that. We have this vast, endless ocean of genetic sequences, the raw text of life, but we're essentially flying blind when it comes to the 3D shape of the other 99.9%. Which brings up the ultimate question. If traditional alignment methods literally require that missing 3D data to find similarities, how on earth do we find functional matches using only the raw, flat, one-dimensional text of an amino acid sequence? Section 2, enter Rprot Vec. This is our sequence-based solution. Rprot Vec, or rapid protein vector, essentially acts as a biological translator. It takes that linear sequence of amino acid letters and predicts the spatial arrangement. It completely bypasses that grueling 3D rendering requirement to give us an accurate TM score, which is just the metric used to evaluate structural similarity without the huge computational cost. And it's a real David versus Goliath story here. Rprot Vec pulls this off with only 7.2 million parameters. That is just 41% of the size of the previous heavyweight model, TM-vec. It needs less data, trains way faster, and, spoiler alert, actually outperforms the heavier alternatives. Section 3, inside the AI architecture. So how exactly does this incredibly lightweight model process this complex biological language so efficiently? Let's look at the extraction pipeline. It might seem a bit complex at first glance, but essentially, the raw sequence goes in, it gets encoded, features are pulled out, and a final vector comes out the other side. This vector is then evaluated using a blistering fast mathematical comparison called cosine similarity. Basically, it's just measuring how closely two vectors point in the exact same direction. Super fast, super efficient. The magic happens in 3 steps. First, the raw amino acid sequence is encoded into high-dimensional vectors based on context. Then, instead of using massive, heavy transformer blocks, it uses a bi-GRU, a bidirectional gated recurrent unit. This reads the sequence both forwards and backwards to grasp the full global context. Finally, a multi-scale CNN zeroes in to capture the local, fragment-level details. That CNN step is absolutely brilliant. It uses parallel pathways with different sized convolution kernels, specifically sizes 3 and 7. You can think of them like magnifying glasses with different zoom levels. They scan for important protein fragments of varying lengths, ensuring absolutely no vital local structural clues missed before outputting that final vector. Section 4, putting models to the test. Okay, so the architecture sounds incredibly smart on paper, but we need to see how it actually handles the real data. And the results are crucial. Despite being less than half the size, Rprot Vec drastically outperforms both the remote and locally trained versions of the massive TM-vec model. We're talking about a significantly lower average prediction error, just 0.0561 across all structural similarity intervals. When you map the predicted scores against the actual scores, the proof is striking. Our Rprot Vec model's predictions cluster incredibly tight to the ideal mark. On the flip side, the competitor model shows a really messy scatter, particularly in the lower ranges, where it's actually falsely predicting similarities between totally unrelated proteins. Yikes. And the accuracy gets even better in what we call the homologous region, meaning proteins that share a common evolutionary origin. In this critical zone, Rprot Vec hits a 65.3% accurate prediction rate. It's exceptionally good at reliably identifying proteins that likely share similar biological functions. What's really fascinating here is that the AI's predicted structure perfectly mirrors the true structural score, while simple sequence identity completely falls flat. This proves the model has actually learned the 3D structural rules, not just basic text matching. It's uncovering hidden, complex relationships that traditional alignment misses entirely. Section 5, Accelerating Drug Repurposing. Now let's transition from AI testing to a high-stakes real-world application, finding new, safe uses for existing pharmaceutical drugs and doing it fast. By feeding known drug sequences into Rprot Vec, we can map out hidden structural similarities. Imagine looking at a heat map, where the intense, deep red spots indicate totally different existing drugs that share underlying structures, meaning they might actually have overlapping medical applications. The model basically played detective here. For example, it linked ecallantide, which is a highly specific treatment for a condition called angioedema, with apertinin, a broad-spectrum drug used to prevent surgical blood loss. The AI accurately recognized that despite entirely different uses, they share profound structural similarities. They both act as serine protease inhibitors, which are enzymes that essentially act as molecular brakes in the body. Section 6, the future of discovery. So what is the big takeaway from this explainer and the massive success of this model? Rprot Vec gives the scientific community a lightweight, blisteringly fast tool. Because it evaluates vector similarities mathematically, it scales like you wouldn't believe. Plus, the creators actually released their 3 curated training datasets to the public, throwing the doors completely open for global researchers to build on this work without having to start from scratch. And this right here is where the real magic happens. By simply running raw, unannotated sequences against known drug databases, researchers can instantly spot red-hot candidate molecules. We now have a way to map that 99.9% of biological dark matter that currently lacks 3D structures. With AI finally breaking through the protein structure bottleneck, saving just untold amounts of computational time and money, it leaves us with one incredibly thrilling question. What unknown cures are already hiding in plain sight, just waiting to be discovered within our vast, unmapped genetic databases?